For today's lesson, we are going to be looking at power functions. Here are some examples of different power functions. Notice that a power function differs from an exponential function in that the function is not raised to the power of x, rather it is raised to an actual constant power. And you can see that in this first one, it's raised to the third, and this one is raised to the second. This one over here is raised to the first, and here we have a function with some additional transformations raised to the fifth. So let's look at a few more and what that means graphically. So in this situation, what you should do is pause this video and graph these parent functions. And then in your mind think about what is the difference between these two sets of power functions. On the left we have y1, 2, and 3 all raised to an even power, and on the right 4, 5, and 6 are all raised to an odd power. You can graph these on the same graph if you like. If you noticed, these even-powered functions all graph like a quadratic in a way. The end behavior is the same whether you're going towards negative infinity or positive infinity. Whereas these odd ones here look more like a cubic. So we have different end behaviors. When you're going towards negative infinity, the end behavior goes one way. Whereas when you're going towards positive infinity, the end behavior goes a different way. So think about these differences. Also look at these key points. These are very similar, again, to a quadratic, which you think about is raised to the second power, as well as a cubic, which is raised to the third power. These are types of power functions. Our key points are always going to be 0, 0, negative 1, 1, and positive 1, 1, whereas in the odd power functions, we have the negative 1, 0, 0, and positive 1, positive 1. Let's go ahead and take what we know with transformations and vertex and functions in order to graph this function. First, let's go ahead and find the vertex in this function. Well, it's written a little differently than what we're used to, but we know that the vertex is hk. So we need to find the transformation along the horizontal or x-axis, and that's going to be in the parentheses with x. So we know that in this case it's going to be opposite h, so it's going to be positive 1. How about k? What is our transformation vertically? Well, normally we look for what's plus or minus at the end, but it's written first. So we have a 4. We could very easily switch that and write it at the end as plus 4. So we know that our vertical transformation is going to be a shift up a 4. Therefore, our vertex is going to be at 1, 4. Now because we just explored the difference between the even and the odd power functions, this being an even, we know that it's going to form a U. We also know that it's going to open down, and that's because we have a negative out here in front of the 2. So let's go ahead and set up some key points and adjust those for our transformations. Here we're starting with our key points for an even power function. Now let's think about our transformations. So we have this x minus 1. We know that was actually a shift to the right. So we will have x plus 1. We'll adjust all of our x coordinate key points to the right by 1. Now how about our other transformations? We have a negative, that's a reflection. And then we have a 2 here, that's a stretch of 2. Plus, we know that we are shifting up 4. So if we put all those together, we have negative 2y plus 4. Let's go ahead and adjust our key points for these transformations. That would give us a 0, 1, and 2 for x. And then for y, we would have a 2, 4, and a 2. If we plot these points, we end up with this quadratic here. So we have shifted to the right 1, we've shifted up 4, we've reflected, and we have stretched by a power of 2. Now let's state the domain and the range. So what is our domain? Well, remember that these end behaviors will continue down and to the right forever. So our domain is going to be negative infinity to positive infinity. How about the range? Well, our range is going to be down here, negative infinity, but then we're only going to go up to 4. So for our range, we'll have negative infinity all the way up to 4, and we do include the 4, so we need that bracket. Let's try one more. Why don't you pause the video and see if you can do this on your own, and then we'll come back together. For this problem, I get a vertex of 2, 0, because we have a shift right of 2. Remember, that's opposite h. We did not shift up or down, so 2, 0. Our key points have changed a little bit. Because it's an odd power function, our key points start off at -1, -1, instead of -1, +1. Now if we apply these transformations, we get 1, 2, and 3 here, and then for y, this changes, our signs become opposite. Let's go ahead and graph this and see what it looks like. So here we are with our vertex. We have a point at 1, 1, and we have a point at 3, -1 down here. Let's state our domain and our range. For these odd functions, you can see the domain and range will always be negative infinity to positive infinity. We're going to go up and to the left forever, and we're going to go down and to the right forever as well. All right, let's move on and try something a little bit different. What happens if we just get a set of key points? So we've collected data, statistics in other words. How do you know if a power model is going to be a good fit for this table of data? Well, there's some steps we're going to run through in order to determine this. The first step is to go ahead and find a power model for the original data. In this case, here's our original data, which gives the mean distance from the sun, that's x, and the period, which is y, in Earth years of the 6 planets that are closest to the sun. We can find a power model either by using power regression on our calculator or by doing it manually. So make sure you can do both. Let's go ahead and do it manually just so that you know how to do that. The first thing is to pick any 2 points from our table of data. So I picked 1, 1 because that was probably the most simplest, and then I randomly picked another point. What I want to do, here's my power model. Y equals a times x raised to the b power. A, remember, is a constant, and so is b. We have to find those. So I'm going to create 2 equations and then use systems of equations to help me to solve to find my power model. My first equation then I'll use with the 1, 1. Let's go ahead and plug in some points. Here I've created 2 equations where I've plugged in my x and y value. I've substituted those in for x and y. So what am I going to do with these? Well, let's go ahead and solve by substitution. So I'm going to solve for a in this first equation. Now let's give ourselves a little bit more room here, and we can do this together. So in order to solve by a in this first equation, I would need to divide everything by 1 to the b power. So I will end up with 1 over 1 raised to the b power. That'll give me my a. Now this can be substituted in for a into my second equation. When I do that, I get 1 over 1 to the b power times 1.524 raised to the b power. Since these are to the same exponents, I can divide them out and simplify. Simplifying this, 1.524 divided by 1 is just 1.524, and then 1.524 to the b is times 1 is the same thing. So how do we solve this to find b? Because ultimately, in a power function, we need a value for b. Well, if you remember back when you did logarithms, we can take the logarithm of this base, 1.524, multiply both sides by that. So we would have the log of 1.524 of 1.524 to the b. So basically what I've done is I've multiplied both sides by this log of base 1.524. And the reason is, if you remember, the log of a base to the same number just gives you 1. And remember, we have the power rule that this b can come down and become a factor. So what we really have on this side is b times 1, and that is just b. Now how do we solve something like this? Well, this we use the change of base formula, and what that means is we take the log of this number here, 1.881, and divide it by the log of the base, 1.524. Remember that the base always stays in the base or the bottom. That can help you. This is our change of base rule. If we do that and we put that in our calculators, we find that b is equal to approximately 1.5. So how do we use this now to get a? Remember, if we go back and we look at our power function, it's written in this form, y equals a times x to the b. We know that b is going to be approximately 1.5, but we still need to find a. Well, remember, this is just like substitution, so we now know what b is. We can plug it into this equation here in order to find a. To do that, we'll go ahead and take 1 divided by 1 to the 1.5, and that equals a. If you take 1 to the 1.5 power, that's just 1, and 1 divided by 1 is 1, so now we know that a is 1. You can also think of 1 to the 1/2 power as 1 to the 3/2 power. And if you remember our fractional exponents, 2 means we take the square root of 1 and raise it to the 3rd power. The square root of 1 is just 1, and 1 to the 3rd power is still 1. Going back to our problem then, we now have our equation. So it's going to equal y equals x to the 1/5 power. So here's our power model. That's a rather long way to get it. Again, you could use regression to help you, but make sure that you can do both. So what's our second step? Now we need to use a calculator to create a new table of values by taking the natural log of each value. The nice thing about logarithms is they can take something, if you remember, that has a multiplicative relationship and turn it into an additive relationship. It can also do that with power and exponential functions. It can take those relationships and turn them into a linear relationship. So if we take the natural log of 0.387, for example, so if I take 0.387 times the natural log, I get this number, negative 0.949, which is in my table. And I've done that with all these numbers to create a new table. So the third step then is to go ahead and plot these new points. If you notice when we plot them, these points all lie very close to a line. In fact, they all lie on a line. This is one way to help you understand if a power model is indeed a good fit. So why do we need to know this? Well, let's analyze power models for a minute. Power functions can be difficult to recognize in modeling situations. You might have a graph, and here's an example of a power model versus an exponential model, and you can see that the trends look very much alike. So how do you know the difference? It can also be confused with logarithmic functions. And here's the good news. When the differences between the models are this small, it doesn't matter which one you use. You only run into trouble when you are attempting to extrapolate far beyond this closed-in data set. So here's an example of where we had some problems. When we had the spread of HIV virus a long time ago, early in the epidemic, the number of cases over time looked essentially like an exponential growth model, when in fact it wasn't, it was a power function. So, using that exponential model, from which the researchers thought it resembled, they ended up overestimating the number of cases that they expected to occur in the upcoming years, and this resulted in overestimates in the necessary hospital space, drug production, etc. For this particular problem that we just completed, I've done a regression as both a power model and an exponential model, and you can see that they are very similar. In fact, they overlap here with this data point at 1, 1. But you can see that the curves could be confused But one other way that you can determine which model best fits is by looking at the coefficient of correlation. For the power function, you'll notice it's a perfect 1. And we could see that when we converted everything to a natural log back here. These data points fall exactly, all of them, right on that line. Whereas with our exponential model, our correlation coefficient is actually quite high, 0.9398, but it's not as perfect as the power function. So again, power regression, if you do that on your calculator, can give you that correlation coefficient and help you determine which model best suits your data. And this concludes our lesson today on power functions. So hopefully after today, you can graph these functions as well as recognize if a model of data is a power function or not.